I'm very happy to introduce Ashutosh Saxena, who is a PhD student from Stanford University visiting us today. Ashutosh has been working with Professor Andrew Ng at Stanford on very exciting work on learning 3D structure from single images and also on robot manipulation and navigation, right? So without further ado, I give the mic to Ashutosh.
Hi, I am Ashutosh, and I will talk about how you can get the information present in a single image to do amazing things. For example, if you have a single image like this, the goal of this talk will be roughly around how can you obtain a depth map from this image. A depth map is a map in which the color at each point gives you the depth value at each point in the image. For example, yellow points are closer, and red points are in the middle, and white and blue points are farther away. Now, let's first look at how do humans perceive depth. There are a couple of different algorithms that humans use for perceiving depth. First of them is stereo vision, in which you take two images and you compute the differences between disparity between two images. So basically, the humans have two eyes. So from the two eyes, you look at something from two different viewpoints, so you can get a sense of depth. The second one is motion parallax, which means that if I look at a scene from this point, and then I move around and look at the scene from a different point, then you will get some parallax. The positions of the objects will change, so you can estimate depth. The third one is focus defocus, which means if I focus on a certain point in the image, the other parts of the image will become blurry. So that also gives a sense of depth. One of the last and the most important of the cues is monocular cues, which means even if I close my eye, or if I look at a single image, I can understand the image completely. I can tell how far each point is in the image, and so on. So in the last few decades, very good computational algorithms have been developed for many of these properties, like stereo vision, structure for motion. Structure for motion is the one in which you take multiple images from a camera, and you can stitch scenes together. Actually, Jana Kosaka was working on this sitting there. And focus defocus, there were some algorithms in 1995. However, all of these algorithms take at least two images to compute a depth map. They require two images to get a sense of the 3D structure. What happens if you only have a single image? Right now, there are no algorithms that can take a single image and compute a depth map out of it. Computing depth map from a single image is hard because local properties are not enough for depth estimation. Let me ask you, what is the depth of these patches? It's really hard to tell because you cannot see anything. But if I tell you the whole image, then you can understand the relation of those patches with other things and tell how far those patches is. So the one important point to keep in mind is that to understand the image, you have to look at it as a whole. You have to understand its relation of with other parts of the image. So relation of the sky with respect to the trees, with respect to the ground, and so on. So we use a lot of monocular cues used for depth perception. So if we look at a single image, what do we look at? If we see a consistent texture in the image, for example, in a grass field or in a farm like this, and if there are two patches, one here and one here, we can look at the local properties of these patches, look at how the lines converge in the image to tell if that patch is closer or farther away. This is similar to the property that you see usually in railway tracks, that railway tracks will converge towards infinity. Now let's look at another image. Let's say you have an image of a panorama like this, scene of mountains. And how do we estimate depth from this image? If we look at two patches, we will notice that the patch which is farther away is hazy or bluish as compared to the patch which is closer. So by looking at the color or blurriness or haziness in the image, we can tell how far that patch was in the image. There are many other cues that we also use, which are based on shading and focus and defocus. Some other cues are known object size. If you look at this image of a beach, then you will notice there are known objects that you can see in the image. For example, these buildings, these people. And if you look at each of these people, then you can infer how far they are, because you know people are roughly of the same size. So if a person is farther away, that he or she will be smaller in the image as compared to a person which is bigger in the image, and therefore is closer. So all of these cues give like weak information about the depth. So in our algorithm, we will put all of these cues together to try to get information from each of them and also capture the information between different parts of the image. So to start, what we do is what most of the computer vision algorithm does. We will compute some features that try to capture some of these cues. We will start by computing, convolving the image with certain features. These are basically edges in different directions and texture of the images. And then to get some more global information, we will append the features of the patch with the features nearby. So this basic, many of these monocular cues will be captured in these image features, which will make the bottommost layer of our algorithm called Markov Random Field. The basic idea here would be that given these image features, we will model the relations between image features and depth at the points in the image, and relation between different parts of the image using a machine learning techniques known as Markov Random Field. So machine learning is about given a data and some labels, you can infer the relationship between them. In this case, what we are trying to do is to infer the relation between image features and the depth at each point in the image. So those are our labels. And we are using supervised learning for this purpose. And we will be using some laser data. So basically, we have these image features at each point in the image. And our goal is to infer the depth at each point in the image. And we will be modeling many relations, such as the relation between image features and depth, the relation between nearby points in the image. For example, if I look at, let's say, this image, then you can see that on this wall, that two nearby points are more likely to have similar depth as compared to two other points which are farther away. And we will do that at multiple scales. So because even if you reduce the image to a smaller size, you can still get a sense of the 3D structure. So this is the probabilistic model, the machine learning algorithm. Here what we are doing is we are modeling the depth at a point in the image as a function of the image features. And we are also modeling the relation between depths at different points in the image. So what we are saying is that the depth at an image is dependent somewhat on the image features, and the depths of nearby points are also closely related. This is modeled by the second term. I will skip over this. Now, let's look at this image. If we notice the patches A and B, they are at different points in the image, so their depths are likely to be dissimilar as compared to patches B and C, which lie on the same building, and their depths are likely to be similar. So what is happening here is that if there is no edge between 2 points in the image, and if the texture of the 2 points is similar, then those points are more likely to be at the same depth. So we will also model these properties. That is shown here. So if we consider 2 points in the image, for example, 2 points on this wall. So both of the points on the wall are whitish, so they are more likely to have similar depths as compared to a point, let's say over there, the boundary between floor and wall, which has different color and has the edge between them. So those points are likely to have different depths or have a boundary between them. So we put all of this in our machine learning algorithm. And what we do now is we have a robot that can drive around and collect these images. So these are the images, and these are the ground truth depth map collected using the laser scanner. So we have a laser scanner. A laser scanner gives you the actual depth at a point in the image. For example, Google has trucks driving around with lasers and cameras mounted on it, which they probably are going to use for street maps. Once we have these images, we will use the algorithm that we described to correlate. Yeah, go ahead.
It seems like the depth map is quite a bit coarser than the image.
Yes, so images are usually of more than 1000 by 1000 resolution, and the depth map is usually lesser than 200 by 200 depth points.
So, for example, if you had a sky classifier working from the image, you could probably get a finer model of the trees.
Say that again?
If you had a sky classifier working from the image, then you'd have a more refined model of the foliage.
So the problem we are addressing is really hard to get minute details right now in the images. So we are looking at how to get a coarse 3D model that looks good and it's correct. So I didn't get your question actually correct completely.
If we had a classifier for sky in the image, then we could cut out very precise outlines for branches and leaves in the depth map.
Yeah, sure. We actually don't need a full resolution depth map for that purpose because you can use image to build a high resolution depth map if you need to. So after we train our learning algorithm on this data, the image and the ground truth depth map, let's see how it performed on some test images. So this is the original image that was taken from a usual digital camera. And this is the ground truth depth map collected from the laser scanner. And this is the output of our learning algorithm. So here yellow points are closer, white is farther away. You can see that the algorithm makes some obvious mistakes, like it thinks that these trees, which are shown correctly in the laser scanner, are actually not there. This is another example of the tree ground truth depth map and the estimated depth map from the machine learning algorithm.
I don't know, I can interpret the top row there. So there's a sort of on the left, the estimated is this blue blob, which seems to correspond to that building on the left, which is not in your ground truth.
So the laser scanner, the best laser scanner that you can get reasonably gives depths only up to 80 meters. So there is noise in the training set. So laser scanner completely misses this building because it's just about 80 something meters away. So
The estimated what you see is some depth, but that depth might be quite wrong.
it turns out
something, but it might not necessarily reflect the depth correctly.
it turns out that it actually extrapolated in this particular case. So it's correct, but correct in the sense it definitely has some error.
It looks like from these images that the laser scanner and the camera are actually taken from quite different perspectives on the robot. Do you sort of do anything to sort of compensate?
Yeah, so we have a model which transforms the coordinate system of the laser to the image frame.
Okay.
Actually, these two particular cases, they are exactly taken from the same perspective. This is after transformation.
Okay.
So the differences you might see are only because the resolutions are quite different in these two cases.
Were these exact images in the training data or very similar ones?
So in these particular images, which I'm going to show this slide and the next slide, they were taken in Stanford University, but in different physical locations. And they were not in the training set, definitely. Some more examples. This is a tree structure and ground truth depth map, the bush nearby, the tree in the background, and the estimated depth map. It makes some mistakes, obviously. It thinks that this bush is actually sort of connected while there's a sharp boundary there and it misses the trunk of the trees. This is another example, a building with some trees. And this is the estimated depth map. This is the ground truth depth map over here.
So I have a question about the features. I'm not sure, I might get a little more into details because it seemed that you use two kinds of features. One is evidence of patches, right, the texture. And another one is on the edges where the difference in color and presence of edges.
Yeah.
Is that all the features that you use? And also it seemed that in the equation you wrote, the features are combined as a linear combination. So what does that mean when you have, how is that?
So so there are basically two types of features. Let's go back. So the features are basically computed from by applying these image filters to the image. These image filters are edges and texture properties, which we apply to each patch in the image. But that doesn't give enough information.
So these are overlapping patches.
So these are overlapping patches. For example, what contains the most information is how the features change as you move in the patch. So if I'm looking at a grass field, the patch on the top of a particular patch will change in a particular way because the parallel lines are converging, so there will be a shift. So appending a patch with its top neighbor would give some sense of depth. And doing that at multiple scales also gives some sense of depth. For example, if there is a blue patch, and it's a small one, and it's less likely to be sky as compared to if the same blue thing shows up in multiple scales and so on. Similarly, if there is let's say, a particular feature, for example, a tree feature over there, so that could show up in different scales depending on the size of the tree. That's the first feature we use. Another question was like, how can we believe that these features are linearly related to the depth? The answer is, as long as you have lots and lots of features, there is some relation that the machine learning algorithm figures out. There's some intuition on why does it relate to depth. It's because we are computing texture energies and gradients, so there is some relation, but it doesn't matter actually what features you use. Maybe if you just throw in the raw pixel values and you have enough data, you will still get some sense of depth. The second type of features are features that look at how the texture changes between two neighboring patches, and they help you get some boundaries like this one. So this blue, there is a sharper boundary as you go to the white for the building. All right, this is an image of the corridor, so cannot really see anything in the image, but there is a corridor and there are some walls. And this is the ground truth depth map. You can see the corridor going in this direction. Blue is farther away. And this is the estimated depth map from that image.
You estimate the metric error of your depth maps?
Instead of showing the image.
Yeah, so I will go to that right now. Yeah. So this is another example which we have downloaded images from the internet. So this is the image downloaded from the internet, and the one below is the estimated depth map. So there is a rock structure here, and there is a house in the background. So you can see ground, that rock structure comes up, and the house in the background. Similarly, there's a street view in the depth map, this night scene in the depth map, this mountain scene in the depth map. Now note that these images are quite different from the ones trained on. We didn't have any of these images, even similar images in the training set. In more quantitative evaluation, we have the laser data, so we can have a holdout test set, and we can compute how accurately is our algorithm predicting the depth. So this is the baseline. The errors are in log scale. The reason is if you are looking at a depth of 80 meters, then error of 10 meters at 80 meters is same as an error of 1 meter at 8 meters. The errors are multiplicative in nature. So what we want to emphasize here are the log errors in depth. So here we show the baseline is 0.295, and our best model gives an error of 0.132, which corresponds to an error of roughly 27% in the depth map, which means if something is at 100 meters, roughly the error will be mostly between 75 to 130 meters most of the time. In contemporary work, some of you might know the work of Hoem et al., in which they were producing photo pop-ups by folding the image at ground vertical boundaries. They do not produce correct depth estimates. They mostly produce good flythroughs in their 2005 paper. Now let's go a step further. Let's say we have this one image. And this is the ground truth depth map for that we collected using laser scanner. What we get from the monocular algorithm is a very coarse depth map like this one. And it makes certain mistakes. Like we cannot expect the monocular algorithm to work 100% of the time. For example, it misses pillars in this case. Now let's say we have a stereo camera that many of the robots have, or any other scanner, maybe a laser scanner. Then you get some other depth values, but they make also mistakes. For example, the stereo vision completely fails in these black areas because of this reflection and no texture. So what we do is we extend our algorithm to also consider the monocular cues as well as the stereo cues, and we combine them together to produce a better depth map. This turns out to be more accurate than either one of these. Here are some numbers for this. So the baseline error was 0.31 on a standard stereo data set, and the monocular algorithm gave 0.09, And the stereo plus monocular algorithm gave better results than either one of those.
Monocular, so that's what you had in the previous table.
Yeah, so this is 0.090 is the monocular case. So that's a monocular only algorithm.
That number is not the same.
Yeah, the data is different. So in this data, the variation, it was more indoor images and closed ranges images, so the number changes.
And you combine the two methods by connecting the images from the stereo into your
Yeah, so we take the evidence from the monocular features as well as the stereo, put that all into the Markov Random Field, and yeah, we use both of evidence from both of the cases.
How long does the inference run?
So in this particular algorithm, the inference runs in about 4 to 5 seconds. That was unoptimized code in MATLAB, research level code in MATLAB.
When you go back to the previous slide, the stereo failed dramatically in these start areas. Why does your method not fail so dramatically? Is there some continuity?
So the stereo
constraint?
method is only based on triangulation. It looks at a pixel and some small neighborhood around it, and it looks at the same feature in another image and tries to compute disparity. But let's look at this area. So there was supposed to be a corresponding image, which I am not showing here. But this image is reflection. So if you move, the reflection also moves with you. And in those cases, the stereo completely fails. Further, in any cases where there is no texture, then the stereo would also fail. On the other hand, we are not dependent on this triangulation properties. We are rather dependent on some global structure of the image or some connected properties. For example, if there was no strong feature in this part of the image, then I would get evidence from other parts of the image, and that information will propagate in to help it out.
So it's sort of a built-in continuity.
Continuity constraints in there.
So when you say stereo, you mean stereo without global inference, right?
Yeah, stereo without global inference. Actually, I have a small link here in which we also show that we also beat the stereo with global inference by some number. I will skip over that. Let's go to more interesting parts. So right now, so far, this was our old work. We are only able to get very coarse depth maps. You see the depth maps are blurry. They're not that accurate. And what if we want to really get accurate 3D models? Starting from this, taking some ideas from this depth map. In this approach, we notice the fact that most of the scenes around us are composed of small planes. So if we over-segment the image segmentation is an algorithm in which pixels of similar color and texture are grouped together. So each one of these portions you see are supposed to be pixels of similar color and texture. Now, because they are small planes, most of the time our assumption works out that these small patches in the image lie on a same plane. For example, this patch lies on a ground, this patch lies on a trunk of a tree, and so on. So in our next model, our representation would be these small segments in the image, and our goal would be to infer the depth and orientation of these small patches, which means if I look at a small patch, let's say a small patch on this speaker, then I want to infer how far that speaker is and what's the orientation of that small patch on the speaker. So that would be our variables. Learning 3D structure from an image is a degenerate problem in that if I give you an image might represent an infinite number of 3D models because it's a projection of the 3D world into the image plane. So we have to make certain assumptions to be able to get 3D models out of it. So one of the assumptions we talked about was vanishing points, in which we said, hey, there are some grass fields which are converging towards infinity, or if you look at a road, then the edges of the roads are parallel, or the railway tracks are parallel. But as they go far away, they start converging towards the horizon. So that is one of the assumptions that was first made by Piccioli et al. In 1996. There are other assumptions that were made. For example, shape from shading and texture work. So if you take an image, you can look at the shadows or the texture of the image and assume that an image is only made up of one type of texture. So if you look at let's say a grass field, and if you assume that the whole image is made up of grass, and the texture of the grass is consistent as you move around, then you can get some sense of depth because the texture would become smaller as you go farther away. So this assumption was made in 1999 by Zhang et al. there are some other assumptions you can make. You can say, hey, everything in the world is made up of a ground and a vertical plane. So that works well in corridors, which was worked in our leg by Delage et al. And by Hoem et al., which is a photo pop-up work, in which most of the images, they claim, are made up of a horizontal ground and some vertical walls. But making such assumptions fails to generalize. Like if you are relying on one of these assumptions, then it doesn't work on all the images. For example, there are no parallel lines in this image. So it works on a railway track image, but how would it work on this image? Ground vertical assumption doesn't work on this image. We have a mountain which has slopes, a tree which has different branches. That doesn't work. So in our next model, we will extend the approach which we just discussed and say we will not make any explicit assumptions about the scene. Rather, we would rely on data and some intrinsic properties of the scenes to estimate the 3D structure. So in our new algorithm, we again start similarly. We take an image like this one, and we divide the image into small segments. So this time our representations is not each point in the image, but rather they are superpixels in the image. And we will compute superpixels or small patches, features for small patches in the image. Now the grid might be irregular because we don't know how the segments are turning out to be. So we take an image, we get it we over-segment it to get something called superpixels, and for each of these small patches, we will compute similar features, texture-based features, and append them with the features of a small patch above it, with feature of small patches below it, and so on. We also use some superpixel shape features, which means what is the shape of these superpixels? If this small patch or superpixel is larger, and it's in the top part of the image, then it's more likely to be sky as compared to these small patches, which are usually turn out to be the case in a tree because trees are less uniform and so on.
I didn't understand whether the features were being computed back on the raw image or whether the features are only being computed within this superpixel.
So they are only computed within the superpixel, and they are shape features for the superpixel. But the important thing is they are appended with the features of the superpixel above it and superpixel below it, right and left, and at different scales.
So the features are computed in patches or already at these irregular regions?
Irregular regions. And they're normalized depending on the size of the region. So this is not really accurate representations or rectangles. They are actually irregular regions, like shown in this particular image on the right. All right, now what do we want to infer? We want to infer the plane parameters. The plane parameters tell you the depth and orientation of the image. Remember, to represent a plane in 3D, you need 3 values to estimate its complete position and orientation. And those values are called alpha. So if this is the camera center, and we are interested in knowing the depth and orientation of this plane, then we represent this plane by plane parameter alpha, and the distance of the plane from the camera center, of the plane from the camera center, is given by 1 by norm of alpha. You don't need to worry about mathematical details, but this is just a representation. The idea is, given these superpixels, we want to infer depth and orientation of each of these planes. And now if we have location and orientation of each of the planes, then we can use just simple computer graphics technique to paste the texture of the image onto these small planes and get some cool looking models. So now that you have this location of small planes, then we will have a 3D mesh which could be used to estimate So what are the properties that we want to capture in this image? Remember, last time we captured 2 properties, the relation between image features and depth, and the second property was relation between nearby points. But the images and the scenes, there are many other properties that we might want to capture. So let's look at this image and look at this particular area of the image. We will notice that if there are 2 small patches in the image, if they look similar, then they are more likely to be coplanar as compared to two patches B and C, which look different and have an edge between them, and they are less likely to be coplanar. Remember, when I say there is an edge between them and they look similar, I'm not hard coding any of this information. I'm just relying on data to learn what is the meaning of looking different. So that's why it becomes robust in many situations. Now, where to make this coplanar or where not to make this coplanar, that is inferred by using, again, machine learning techniques, which basically take an image, compute some features, and learn this sort of edge image or occlusion boundary image from an image. So the black areas represent the places where the planes are more likely to be folded, not coplanar, or they are likely to be occluded, which means like there is an edge between my hand and me. So those boundaries would represent those points. So now we have a feature representation from which we just inferred some boundaries between the edges. And we also put in some other constraints in the images. For example, if you see a long line in the image, for example, a sidewalk, a line in the building, or a railway track, then if that line is long and straight in 2 dimensions, then it's more likely to be long and it's more likely to be a straight line in 3 dimensions. So it's less likely that this image would turn out, this is the camera center, and it's less likely that this line would turn out to be curved. It's more likely that it would be a straight line in the 3D world. We also put that constraint in the MRF, Markov Random Field. So now we are modeling the following relations. The relation between image features and edges, the relation between image features and the depth and orientation of the small patches. And these relations represent if the nearby planes are coplanar or not coplanar. So, and the strength of these edges, like how strongly do you want to make 2 things coplanar, is told by these edges. So in places where there is an edge, you don't want to make them coplanar. And if there's no edge and they look completely different, then these edges would be stronger and they would look coplanar. Some of you might have worked with energy minimization frameworks in which you are trying to minimize competing energies. So this is sort of that. So there are 3 different energies. One energy says, I want to have the depth related to image features and I want to minimize that. Something says, I want to minimize the relation between features and edges. And this one says, hey, I want to keep the planes coplanar. And these all compete with each other. And how to set those parameters, they are all learned from the data using machine learning algorithms. This is a summary. We have image features that gives you boundaries, and these 2 things combined give you the depth or the plane parameters. Let's say you also have some object recognition algorithm. They are very good computer vision algorithms that are developed by vision community, in which given an image, you can find some objects like these people. So you can put these constraints also in the MRF in more like a grammar sort of framework. So if you find that something is a person and something is a ground, then you can say things like the person is attached to the ground. So the plane on which the person lies should be attached to the ground here. So those 2 planes should be attached to each other. Or if you know that something is a person and something is a ground, then there is no way that the person could be below the ground. So you can put that constraint in the MRF also. Again, the output of the classifier is not correct always. So you're not hard coding these constraints. You are putting them as a soft constraint in the Markov Random Field, as another energy in the Markov Random Field. So all of these things go together in this probabilistic model. So these products basically represent different energies, which we just discussed. Don't look at the math, but just look at the fact that they are products of different energies. So the first one says the relation between the depths and the features. The second one is a product of different things like coplanarity constraints, the information from objects, and so on. It turns out that the way we model this, the inference in this model could be done by using a fast linear program, which is really efficient and works in a couple of seconds. So yeah.
What's the size of the matrix in the linear program relative to the image? Is it the size of the image? Or
So the trick here is that we are using super pixels or small segments in the image, not pixels. So it's not in thousands. I think the total number of variables is roughly 100,000.
So the matrix is 100,000 by 100,000?
100,000 by number of 100,000 by, let's say, 3,000. So 500 features and other properties, which are some 4,000.
So going back to the comment about the additional knowledge you, like the say person detector, you said you use some constraints, but on the other hand, you're not modeling the uncertainty as to the placement of that person.
Say that again?
You're not modeling the uncertainty with respect to that to the placement of that constraint. So could be that you have some biases, introduce some biases by having, say, a certain kind of person detector that gives only one particular proposal, but not contemplating alternative proposals that that person could do.
Yeah, that is very true. So most of these classifiers are not reliable at all. So if you look at the images uploaded by people on the internet, and we run the best of the classifiers that we have, then they mostly make some errors. So actually we have different classifiers. We can have different kinds of information. For things like cars and people, you have the size of the patches as well. You can put that in. And you have the semantic information that car should be attached to something or should be behind or in front of something. And they again go as soft constraints. So yeah, you don't know the location of the object precisely. So the size of the rectangle that you get from a classifier is also erroneous, and could be biased. But the idea is we are not relying on one specific thing, but rather a plethora of things. So overall, we hope that it would turn out okay. So in summary, these are before we move on to results, yeah, go ahead.
If neighboring regions are similar in appearance, they're likely to be coplanar. If regions that are not neighboring are very similar in appearance, then there's some increased likelihood that they are parallel. Would that be a useful property?
So that we are not modeling right now. Yeah, it's a very important point. If I look at this image, then this part is basically occluding the wall behind it. So the properties of the wall here and the wall here are matching. But they are basically broken by this occlusion, as you say. We are not modeling that right now. Yeah, but that could be built in the framework. We have not done that. So we are modeling these properties in summaries: the relation between image features and depth, coplanarity, connectivity, and collinearity, which means straight lines should be straight, are more likely to be straight in 3D, and the information from known objects. Other than these, we have not made any explicit assumptions about the scene. So hopefully our method will be able to generalize well. So, in a couple of examples, we gave our algorithm this image that we ourselves took on the campus, and this image that was downloaded somewhere from the internet. And let's see what results it gives. So remember, we gave a image that was not seen before in the training set. And once we have the orientation and location of the planes, we pasted the texture from the image onto this 3D model. And you can probably note. Okay, I cannot use my laser pointer when it's Cortana is running, it figures out. But you can see the trees on the right. So you can see the trees on the right top, and the curvature of the trees on this side. Let's look at this image, which we last saw.
Can you add texture?
Can
you remove the texture just to see the depth?
Not from here, but if you go to my website, which is unfortunately down because there were a couple of 100,000 hits, you can see the texture.
I mean, no texture, just remove the texture.
Yeah, you can see it without texture in the shockwave. Yeah, go ahead.
My question is the opposite. Can you add texture? Looking at these scenes in 3D, it seems as if you could add some of the foreground elements to super resolve the background element.
You can add texture into it. What do you mean by that?
Well, I've got a picture of a lawn, and the grass in the foreground is very well resolved. If I think that it's all lawn, then as I zoom into it, I can reproduce the foreground texture to get a very high resolution rendition.
Yeah, that would be an interesting direction to go for. In particular cases, sometimes you cannot see occluded things. So in these examples, what we are seeing is that so for example, if there was a tree in the foreground somewhere, and that would occlude some of the parts of the image, then I might use your method to actually fill information in, because I know it's a parking lot. It looks like a road or a ground. So I can color that texture or that properties inside.
I'm thinking there's a prospect for enhancing even visible regions of the image.
Yeah, possibly. So anyway, so imagine that you are looking at this scene, standing in front of this rock ledge, and you crouch down. So you get a completely different perspective of the model. And you look it from the right, turn left, and come back up. So this is the image of a mountain, which was downloaded from the internet. And you can just move in the image. Look at the skyline of the mountains on the left, and the trees. So it gives you a decent fly-through experience.
The question, do you get basically a symmetric image because the top and bottom are kind of the same?
Not really. Not really, no. Because the sky, in most of the images, the sky is farther away. It's only in indoor images that you see symmetricity on top and bottom. I guess.
But the sky is also reflected, isn't it?
Oh, the important thing to notice is we have one more information that's coming in, which is the location of the pixels in the image. So something is more likely to be sky only if it's in the top part of the image as compared to the bottom.
So even though it looks the same, the classifier handles it differently.
So there are some spatial constraints. For example, the sky could only be in top of certain things and so on. Yeah.
In this case, you've got a very, very convincing reconstruction that actually did reconstruct symmetrical 3D structures on the side of the plane of the water. But in the reconstruction that resulted from the process, is there anything in the plane of the water?
It's mostly a flat plane. This image is actually very surprising to different people. Why doesn't it predict the mountains or the trees here? The reason is that the superpixels are sometimes very long. So cannot use my laser pointer, but there is this lake going on till this point, right? And these superpixels help transmit long-term information that you were talking about. So if there was a small patch here, that would have some evidence transfer here, and that would get back to in this part of the image. So it turns out that these long patches in the image help to correct many of these mistakes. For example, that one. All right, now let's talk about, this is only one image. Now, let's say you have these three images. This one, and this one. Notice that if you take these three images, some parts of these images don't have anything in common. So, I don't know what's wrong with my laser. So this image doesn't have anything in common. There's some parts of this image don't have anything in common with the other two images. The right side of this image, there's nothing common over here. And there are a lot of repeated structures in the images as well. So you might have known some algorithms like Microsoft Photosynth that take multiple images from the web and combine them to make a 3D point cloud, and you can walk through in that area. So, but many of those algorithms such as Photosynth, or the technical name for the structure for motion algorithms, fail in cases where there are repeated structures in the images. For example, they are stereo vision type of algorithms. They basically rely on matching between different images. So if you see something in the image like a pillar, and in another image you also see a pillar, then they are basically think that they are the same point, and you can use triangulation to do something. But in many cases, those algorithms fail if there are repeated structures in the image. So this pillar looks very similar to this pillar. and those algorithms fail completely in different cases. So what we do is we take our monocular algorithm and we throw it in these multiple images to get actually a larger viewpoint, so get larger models like this. So this is a composite model made from 3 images. You don't get a very good reconstruction under the arch because there was little information and there were some rendering problems. Any questions so far?
Faces and stuff.
Faces? Yeah, that's the question I've been.
Does it get, because that's sort of a quite a, feels to me like a different problem, but there's a lot of these things sort of apply to
So, yeah, so potentially there are many applications. You can have faces, you can consider images from aerial images taken from the satellites and different cases. So inherently the algorithm doesn't have any specific problem with learning that. Is that we train the algorithm on data taken with ground images looking forward, so it directly doesn't work on those images, and we haven't tested it on cases like faces or aerial images, so we don't know.
Elaborate a little bit on the difficulties of learning the parameters of some of the other functionals which you use in the later part. So I can see the kind of the depth and feature relationship. But you just skip through it really fast. But if you want to learn this relationship between feature and linearities and feature and coplanarities, what kind of you cannot use the raw depth times. So do you do some kind of
So basically, we had used 2 kinds of training data. That's not in our one of the papers, but this is our sort of future work that we have been doing. So to learn the edges, we have various information. We have images, we have depth map, and we have something called scribbles, which is from the website data that I have. So if the algorithm makes a mistake, then the user can go into the website and fix certain things by scribbling over the images. So you have that data as well. So putting all of that in, you have raw data which tells you which parts look, you think they should be similar or coplanar, and which parts should not be coplanar. Again, we have like 500 to 1,000 of features, and we use the training data to learn edges. One thing that helps quite a lot is it is easy to learn those edges when you have some 3D information as well. Go ahead.
Yeah, so,
how much time do I have, Raghu?
You have 10 more minutes.
Okay.
Do you use a colorization algorithm to propagate your scribbles?
Yes, we use a Markov Random Field type of algorithm. So it propagates depending on how similar uses the image information to propagate the scribbles.
So during the learning, you have 3 different kinds of potentials in this Markov Random Field, right?
Mm-hmm.
How, in what kind of objective do you do? How do you trade them off between each other? Is that learned automatically?
So there are, I think, 2 parameters which are tuned by hand. The meta parameters, all the parameters are learned. So the meta parameters tell how to weight the information from edges versus objects versus features. That possibly it could be learned by cross-validation or by estimating the partition function, but we set it by hand. All the other thousands of parameters are learned. So, yeah.
For each separate of these 3 models, you learn it independently.
Independently, and then we set it.
And then when you merge it.
Recently, we have been trying to iterate and using some variational approaches to learn it, but that's not in the results so far. Yeah.
Since most of the features actually signal changes in depth, it will make more sense to learn a model for depth gradients rather than absolute depth?
It turns out actually the thing that is figuring out the most is gradients in depth. So remember, we have features which are top nearby features, so they're actually sort of encoding changes in depth, because it doesn't matter if you scale the whole model up and down. So in some sense, it is relative depth. Maybe modeling it more explicitly in the MRF could improve performance. That's true. Let me finish up by telling some of the results that we did in 2006. So we asked the users to upload images on a small website. So this is the original image that users uploaded, the first row and the third row. And we used an algorithm to estimate the depth map and build some texture models and took some snapshots. So if this is the original image, this is a screenshot that you see. You can see that the staircase is occluding this balcony over here. This is a night scene, which I showed you earlier. And you can see that the algorithm was never trained on night scene. It still predicts some sort of 3D structure. This is a house taken from a viewpoint on the right of the house. It fails in certain cases like these ones, where although the general trend of the 3D structure is sort of OK, but the texture is stretched down. So it's considered as an incorrect model. More formally, we did the following experiment. Remember, we have laser depth map also for some test images. So we compared various algorithms. Our algorithm, the algorithm by Hoem et al., and our recent algorithm. This experiment was done in November 2006. So the algorithm beats all our earlier algorithms in terms of quantitative error in depth. In terms of internet images, which is a more interesting test case, we did the experiment of that users can rate the models as being correct or incorrect based on some guidelines. So if the model visually looks correct, the planes are in proper places with respect to each other, then that model would be correct, otherwise incorrect. So our model was able to predict quote-unquote correct 3D models for about 65% of the images, of the 588 images on which the experiment was run on, as compared to earlier prior work, which roughly works with 33% of the models and doesn't give you detailed structure and doesn't give you depth either.
Okay, this is what I want to do.
All right, I will brief. And recently, once I have put this algorithm on the website, we have ran this on around 3,000 images. And so far, the performance, as far as the users are rating them, is around 50% of the images. Now we can take these algorithms and apply them in robotics. I will quickly show you two videos. One is the application to robotic navigation. So we can implement a real-time version of the algorithm for this small robotic car, which only has one really cheap small web camera. And the goal of this thing is to just drive around as fast as possible, estimate depths in the scene, and avoid obstacles. So it potentially has some applications in autonomous driving. So remember, the hard part here is that it's only seeing a very blurry image from a cheap web camera and estimating depths in a real time to drive around.
Stop it.
So in this experiment, I'm running around with a handycam and a backpack which contains a laptop and wireless interface to the car. What's that? We have some recordings, yeah. So this is the problem, unsolved problem in robotics. If you don't see anything, you don't know that you're not seeing anything. It's like the negative obstacle problem. So all right, you can apply this to robotic manipulation as well. So it turns out it's a really hard problem in robotics to pick up an object which was never seen before. But we have seen that images contain enough information, so we can use that information to find out the 3D structure of the scene and figure out how to grasp an object that was not seen before. So we tested it on these two robots, on objects that were never seen before, and applied to the problem of grasping objects such as staplers or plates lying around in a kitchen or unloading items from a dishwasher. So this is a video which shows, oops. So this robot is again taking a camera, finding out how does the image looks and figuring out where to grasp it.
What data was this trained on?
So it was trained on object data. So similar algorithm was trained on image features versus what point to grab at. So the labels for what's the best point to grab in an object. And none of these were seen in the training set, by the way. And then we applied it to unload items from a dishwasher. I will skip over this. So it can unload items from a dishwasher. And I will show instead something more relevant for this talk is once you have a 3D model of a scene, then you can automatically plan a path, which is the problem in robotics also. The car has to plan a path to go somewhere. The robotic has to plan a path to grab something. And in this case, you have a 3D model. You have to plan a path for the camera automatically to give you the best viewpoint. Imagine that someone uploads his photo on Flickr or Google Picasa, and you want to make a YouTube video out of it automatically, in which the camera automatically flies and gives you different views of the scene. So let me see if I can get it running. So it takes a 3D model, computes a path based on some properties. All right, so this was work was done with different people. Most importantly, Min Son, on which the 3D reconstruction work is based for reconstruction from single images. Thank you.